altitude of a geosynchronous satellite. And a geosynchronous satellite is a satellite that rotates at the same period of the Earth rotating about its axis, which, as we know, is 24 hours. So we're going to start with our diagram where we can draw the force of gravity as the only force acting on the object. And then we can draw the altitude as h, and then a radius of the Earth, which will be important. Now, as you can see, the satellite rotates in a circle, so we can use the equation for gravity as the centripetal force, which would be mv squared over r. And then we can also use the universal gravitational equation of big G, mass of the Earth, times mass of the satellite over r squared. And then, since these are both equal to the force of gravity, we can set them equal to each other, mv squared over r. And let's clarify now that our total radius of the satellite is the radius of the Earth plus the altitude. So this would be radius of the Earth plus h, and now it's equal to big G, mass of the Earth, mass of the satellite over, and then radius of the Earth plus the altitude squared. And as you can see, some of these values cancel out. The mass of the satellite cancels, and then this radius over here cancels, and this squared cancels, because if you multiplied this over, it would cancel out one of those. And we're left with v squared, that looks like an r, v squared equals big G times mass of the Earth over radius of the Earth plus h. Okay? And then from here, since we're not given a velocity, we're going to want to find that. And the velocity would be the distance over time, and the distance it travels is the circumference over the period of the rotation. And that's 2 pi times the radius, which is radius of the Earth, plus altitude over the period. So if we substitute that in for the velocity, we get 2 pi radius of the Earth plus altitude, this whole thing is going to be squared over the period. So all that is squared, and that's equal to big G, mass of the Earth, over this radius. And then if we square that all, we get, 4 pi squared. This big radius is squared over the period squared. It's equal to big G, mass of the Earth, over this radius. Okay? And then if we multiply all this together, I'm going to draw up here, we get 4 pi squared times this whole radius cubed is equal to, multiply the t squared over, and then we're going to divide by big G, mass of the Earth. And as you can see, this is Kepler's third law, where we just have a modified radius that accounts for the altitude of the satellite. So once we have this, we can start substituting the values that we're given. So 4 pi squared times the radius of the Earth, which is 6,378 kilometers, plus our height, which is what we're trying to solve for, cubed, over big G is 6.67 times 10 to the negative 11th, times the mass of the Earth, which is 5.97 times 10 to the 24th kilograms. Okay, and that's all equal to t squared. And t is 24 hours, but before we put that in, we're going to want to convert it to seconds because the gravitational constant uses seconds. So 24, we're going to multiply by 1 hour equals 60 minutes. 1 minute equals 60 seconds. And with that, we get a time of 8.6400 seconds. Okay, so we can plug that in as 8.64 times 10 to the 4 seconds, and that's squared. Okay, so then when we solve for that, we can multiply these together and move it over to this side, and we're going to be left with h equals the cube root of 6.67 times 10 to the negative 11th times 5.97 times 10 to the 24th times 8.6 times 10 to the, I don't know if this is going to show up. Yeah, well, 4 seconds. We'll include that. Over this 4 pi squared, and then because it's added to the raised to the earth, afterwards we're going to have to subtract a 6.378 kilometers. And then our height is going to be, or our altitude is going to end up being 35.849 times 10 to the 6th, we'll write 3.5 to the 7th meters. And then in kilometers, that gives us 35,849 kilometers, which is roughly 22275.54 miles. So 22,275.54 miles.